Hi and welcome to Physical Attraction. This week I'm going to be presenting you with an episode that would have come out originally in our series on thermodynamics, and it would have closed off our whistle-stop tour of classical thermodynamics with a very, very basic introduction to one of the most fascinating areas in physics and the physics of energy. For whatever reason, it didn't get recorded at the time we did those episodes, which was some years ago now, but I've dusted off the script and re-prepped it, and we're ready to go with the Statistical Mechanics episode. So this episode is called Statistical Mechanics and the Entropy of Information, and it's about a really incredible field of mathematics and physics which I'd heard nothing about before I started studying my degree. I went from not knowing that this existed to counting it as a favourite area of physics, and in some ways it's more generally applicable than things like quantum mechanics and relativity are. Yeah, statistical mechanics deserves more fame for its elegance and for its usefulness, so let's talk about it. But first, it's important to go over some of the stuff specifically from the entropy episode of thermodynamics, because entropy turns out to be a fundamental concept in statistical mechanics. I'm going to go through a somewhat technical definition of entropy, but there are plenty of analogies that are familiar from the world around us that show entropy in action. When you mix dye into water, the dye stays mixed. It doesn't spontaneously unmix. Technically, perhaps it can be done, certainly if you put a lot of energy and effort into the unmixing, gradually separating every dye particle from every water particle and so on. But increasing entropy is certainly a harsh law of the universe. In the same way that you rarely see pool balls bouncing around a table before they come to rest back again in a perfect triangle, we do not often see entropy spontaneously decrease in nature. The arrow of time points in one direction, the direction of disorder. Hopefully, in defining entropy, we can go from these qualitative ideas about things being disordered to talking about how this is really a statement about information, without anyone's heads exploding. First off, though, a rather sick joke from history that amused us all when we studied the subject. It's found as the first page in David Goodstein's book States of Matter, a warning about statistical mechanics. He said, quote, Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it is our turn to study statistical mechanics. Perhaps it will be wise to approach the subject cautiously. We're not going to go into that much depth, and besides, I think it's a lovely theory with very little reason for you to kill yourself over it. You shouldn't do that anyway. In all likelihood, your life is not entirely your own. Or, to quote the great Kimya Dawson, call me up before you're dead and we can make some plans instead. So recall that in our thermodynamics episodes we were talking about thermodynamic systems. Maybe they had a temperature, a volume and a pressure associated with them. These big values of temperature, pressure, volume, they're what's called a macrostate. Macro means big. There are also microstates for a system. To understand this, it's best to go back to our favourite example system, which is atoms of gas running around in a jar. The macrostate is, okay, how many atoms are there? What's the temperature? What's the volume of the gas? What's the pressure that the gas is under? The microstate is, okay, what are the positions and speeds of every single atom in the jar of gas? So you can see there are billions of possible microstates, because each atom of gas could be in all kinds of positions and have all kinds of speeds. But actually, many microstates correspond to a single macrostate. You can have lots of configurations, lots of positions and velocities for atoms, that will still give you the same temperature, pressure, volume and so on when you measure the properties for the gas as a whole. So individual macrostates of these large-scale variables have many, many microstates associated with them. Now each microstate has a certain probability, a certain likeliness to happen, and this too does make sense when you think about it. It's really unlikely that all of the molecules will crash into one molecule at once, making it super hot, or crash into one wall of the jar at once so that there's no pressure on any of the others. Microstates where all of the molecules have a fairly similar energy and whiz around happily are far more likely to occur. They have a higher probability. Just in the same way that if you imagine pool balls dancing around on a table, you far often get some random configuration of balls that have been smashed around the place and lie in various areas, than you do a strange situation where all of the balls are gathered in one corner, for example. Then, the entropy of a macrostate for a system is the number of microstates that macrostate corresponds to. If there are billions of ways of distributing energy amongst the molecules that give you the same temperature, pressure and so on, that's a very high entropy state. If there are only a few ways that you can distribute these things, then the state is low in entropy. And now you can begin to understand what we mean by saying that entropy is like a measure of how disordered things are. Imagine the atoms in the gas again. There are many microstates where they're all just whizzing around randomly with no particular order or reason to what they're doing. But there are fewer microstates where they're all moving in one direction, when you add some order to the system. Again, imagine the pool table as an analogy, how few microstates there are where all of the balls are clustered in a single corner, compared to randomly spread out across the table. The second law of thermodynamics essentially tells us that every process that occurs results in the entropy overall in the universe increasing. If you try to act to make things more ordered in one place, you must increase entropy as a whole in the universe. Take a freezer. It freezes the things inside it, it reduces the thermal energy of the air in that system, and reduces the entropy of the things inside the freezer. But it pumps out heat to the back, and it requires energy to do this. So much heat that you're still increasing the entropy of the universe by running your freezer. Similarly, life. You could almost define life, living beings, as self-replicating structures that reduce entropy within their own structure. But left to its own devices, your body would decay. Little microorganisms would break up the complex structure of your cells. Everything would gradually fall apart. Instead, though, hopefully, you are alive. Through an incredibly complex set of processes in your body, your cells are kept alive. Energy is transmitted around the system. Nutrients flow through the bloodstream. Repair and protection takes place. You're keeping yourself ordered through an unimaginably complex set of operations, and you're keeping entropy from increasing in the region of your own body. But of course, you pay a price for that. It's not free. You need to constantly consume food, water, etc., produce and burn sugars, and you're giving off heat all the time. Maybe if you want to get more poetic and less physicsy, you can see an analogy in the basic processes of life when you go up the pyramid of Maslow's hierarchy of needs. Just as, in order to keep order in your body, you need a constant supply of food and water and nutrients, so to keep order in your mind, you need stimulation, affection from other humans, self-esteem, and so on. Regardless of whether you want to follow the analogy that far, or view things as so simple and mechanistic, we are all machines that move entropy around. You increase the entropy everywhere you go by radiating heat into the environment, and because your body has to obey the laws of physics, the net result of your life, when you consider the entire universe as an isolated system, will be to increase entropy everywhere else by more than you reduce it. By the way, there's a very interesting paradox that's commonly associated with James Clerk Maxwell, famous for Maxwell's equations and electromagnetic theory. This is an attempt to find a contradiction for the second law of thermodynamics, this iron law that entropy in the universe is always increased. Imagine a favourite thermodynamic system. You have a box filled with molecules of gas. There's a partition between two halves of the box, and a little trapdoor that can allow molecules to pass from one half to the other. At first, all the gas in the box is the same temperature. Now Maxwell imagined a little watchful creature, Maxwell's Demon he called it. This creature looks at the molecules that approach the trapdoor. Maxwell's Demon has his own plans for the box. He carefully opens and closes the trapdoor in such a way as to sort the molecules into the different chambers. For example, if he sees a hot molecule in the cold chamber moving quickly, he lets it pass through into the hot chamber. Cold molecules in the hot chamber are also let through to pass into the cold chamber. So he's opening and closing this door to allow the different molecules with the different temperatures to pass through when they are about to bounce into the door. And gradually, just by selectively opening and closing the trapdoor, Maxwell's Demon has created order. He's sorted the hot molecules from the cold. Before Maxwell's Demon, there was a high entropy soup of molecules, gas at the same temperature whizzing around in the box. After Maxwell's Demon and his tricky trapdoor ways, though, there's order. You have a temperature gradient, because you have all of the hot molecules, the ones that have a lot of kinetic energy, they're in one half of the box. And all of the cold molecules, that don't have kinetic energy, they're in the cold part of the box. And once you have this temperature gradient, you have energy that can do useful work. Whichever way you slice it then, Maxwell's Demon has violated the second law of thermodynamics. The new system with a hot box and a cold box has less entropy than the lukewarm box. He's turned some of the random heat from the first box into useful work energy. The Demon, having broken the laws of thermodynamics, could illegally siphon away this extra energy from the system. It could reverse the inevitable increase of entropy everywhere. So it seems like a paradox. In actual fact, though, it turns out that even Maxwell's Demon, a highly idealised system where you can make these perfect observations and lift the drawbridge just in time to allow the molecules through, can't get around the second law of thermodynamics. Even in observing the molecules and opening and closing this trapdoor, Maxwell's Demon is processing information. Observing the molecules and that approach, that requires energy from the demon, as does understanding which ones to allow through. Even if the trapdoor is arbitrarily small, the size of a molecule say, so that moving it doesn't generate much heat, it doesn't matter. Recording the information about the molecules in its brain, or in its computer system, or whatever you want to say, processing the calculations to figure out which molecules to let through, this all requires some physical movement, some physical memory to change. The act of writing, storing, or deleting the memory of the demon requires energy, and this energy that is associated with the information has now been calculated. And it turns out that this alone means that the demon's entropy must increase. The energy it must be supplied with, somehow, is greater than any of the energy it could extract through its tricksy ways. Yet the subtle and beautiful problem of Maxwell's Demon remains an area of fascination and study for statistical mechanics and thermodynamics. Much experimental work focuses on producing things that act like a Maxwell demon, and measuring the entropy associated with them. But even these demons, try as they might, cannot violate the second law. We have these ideas then. Entropy is related to the microstate and macrostates of a system, which tells you everything about the properties of that system. Entropy is always increasing, and physical processes tend to unfurl in a way that maximizes it. What statistical mechanics then does for you is it actually weaponizes these facts, and it lets you turn them into a mathematical formalism that lets you understand the properties of a lot of different systems. So let's talk about the ways that we can approach physical systems. We'll start with our favourite model, gas atoms in a box. One of them is kinetic theory. In kinetic theory, we look at individual molecules. We consider things like their velocities, their momentums, and how they collide. Then you try to calculate things like the pressure by understanding how the molecules collide with the walls of the box. You try to understand how the energy of the system works based on averages over these molecular velocities. In statistical mechanics, though, we start with microstates, and we try and figure out the probabilities associated with them. That way, we can calculate things like the average energy, pressure, and other useful quantities. The laws of statistical mechanics come from saying, imagine we have a system with a lot of different microstates that it can be in, and some set of probabilities of being in each microstate. Then you add in some constraints that come from your knowledge of the system. The simplest possible situation is total ignorance, where you don't know anything about the system at all. Then you use something fancy called the principle of a priori equal probabilities, which is just a fancy way of saying that if you don't know anything about the system at all, you have to assume all microstates are equally likely. And this might seem like it just comes from simple common sense. After all, if you don't know anything about the microstates, it doesn't make sense to favour some of them over the others. But it also comes from the principle of maximising entropy. A system where all microstates are equally likely has the maximum entropy. So there are good reasons to have this as our basic idea. Once you have that assumption, you can start seeing how measurements might change it. Let's say you take a measurement of the system, that you measure its total energy. This then changes your understanding of the probability distribution for the microstates, doesn't it? When you take a measurement, you're effectively looking at the macrostate of the system. If you find out that a system is incredibly hot, then the microstates that are more energetic must be more likely, while the colder ones must be less likely. And that in turn is telling you things about the speeds of the atoms of gas in the box. In other words, this measurement gives you a constraint on the system, on the probability distributions. And you know something else about the system too, that entropy has to be maximised, because that's the second law. So you need to find a probability distribution of microstates that maximises the entropy, while obeying the constraint that comes from the new information you know about the energy of the system. I try not to get too mathematical in these shows because it's really difficult to understand mathematics without visual aids, so I'll just talk a little bit about this type of problem mathematically. If you want the full gory mathematical detail, Blundell and Blundell's Thermodynamics book or Alex Shekhar-Shahin's notes for the A1 module, which are on his website in Oxford, will tell you. But I should warn you, it's degree level maths. So this type of problem is what we call a Lagrange Optimization problem. Maximising one function, the entropy, subject to constraints, which are what we know about the system. You solve these problems using special variables called Lagrange multipliers. Each constraint you add to the system, each piece of information, each measurement of the system that you have, gives you another Lagrange multiplier. It turns out that when you do this, something rather miraculous happens. We have this pretty abstract sounding problem, right? let's maximise entropy subject to the constraint that we have from our measurement on energy. But out pops, as the Lagrange multiplier, a very interesting quantity that has a real physical interpretation. It's the temperature of the system. Similarly, in systems where the number of particles can vary, you can get another Lagrange multiplier, chemical potential, by applying the constraint from measuring the number of particles. Just as the temperature is a measurement of the entropy that you put into a system by adding a little more energy, chemical potential is a measurement of the entropy that you put into the system by adding another particle. A system where the number of particles can change might seem a little arbitrary, but this is the case for photons, for example, where you can have more and fewer being created with different amounts of energy, and also when you have chemical reactions taking place, and the energy levels of the system can be set by how many of the molecules have interacted with each other and combined, or how many have not. You can see, for example, that the fact that some chemical reactions produce heat while others absorb the heat, that there's a whole branch of thermodynamics which explores the balance between two different types of energy flow. One of them is having reacted/unreacted chemicals versus the energy flows associated with heat. Then something even more miraculous drops out of the mathematics. It's called the partition function. The partition function is essentially a sum over all of the possible microstates of the system. It adds up a function that depends on their energies. Specifically, this function is the exponential of minus the energy divided by the energy associated with that temperature. And when you sum those up over all the possible microstates, it tells you some things about your system. For a system in an equilibrium where you can measure the total energy, you can derive the probability of being in a microstate just from the energy of that individual microstate and the temperature of the system. So again, imagine we have our box of atoms, and we know what the energy of that system is in total. If we also know the temperature, then we can actually figure out the probability of any individual microstate manifesting itself. And this does end up making perfect sense. When you apply it to atoms in a gas, it actually just turns into the Maxwellian distribution of velocities, the one that belongs to atoms in equilibrium back in the thermodynamics episodes. It looks a little bit like a Gaussian, a bell curve, with a really, really long tail for high-end velocities that can happen. So you have some average velocity, and then there's a small probability that some molecules get bumped around and they have many, many multiples of that average velocity. And it's centered around a place that increases with increasing temperature. So the higher the temperature, the higher the average velocity of particles in the box. And this shape, this mathematical function that tells you how likely each velocity is to show up, that's the Maxwellian. And if you calculate the partition function for the system of atoms in a box, you end up with the Maxwellian again. But what's really interesting about the partition function is that if you evaluate it, you can calculate the mean energy. After all, a mean average is basically just a weighted sum over probabilities. If you win £10 20% of the time and £1 80% of the time, your average winnings are £2.80, that kind of thing. So once you have the probabilities of being in each microstate, which just depend on temperature, chemical potential, and the energy of the microstate, you can figure out the mean energy. You can calculate other things like chemical potential, pressure, entropy, volume, pretty much anything else you might be interested in, just from this partition function. And all you need for that is to understand the possible microstates and the energies that the system can have, and then measure the temperature. So pretty much everything that you care to know about the system comes from working out the partition function, and then you differentiate it to get all of these other variables. So a great deal of physics just becomes understanding, okay, we have a system here. What are the different microstates that it can occupy, and what are the various energies that they can have? Once we have the microstates and the energies, we can calculate the partition function. Then all you need to know is the temperature, which you can usually measure, and you can write down its internal energy, entropy, and other useful quantities. People have used quantum mechanics to work out the partition function for individual quantum particles in a box, and they were able to rederive all of classical kinetic theory results that way. You can get all of the information about the ideal gas, equations like PV equals nRT, which you probably remember from school, Boyle's law, stuff like that, all variety of different physical systems, just from understanding what the partition function is. One good example is if you have a two-level system, then the energy can be written as plus or minus 1, for example, and you can see that you get a hyperbolic cosine function for the partition function. Then, just by looking at the function, you can see the behaviour of the system, how likely it is to flip into energy level 1 or energy level minus 1. These things can be used to work out magnetic energy levels. You can use it to work out how the two kinds of fundamental particles, bosons and fermions, behave thermodynamically. In fact, most of the best theories of different kinds of magnetism are really just contained in these big lists of partition functions for the systems, and all you have to do for that is to work out what are the different states that the system can be in. What are the different conditions it can have? Where can the different spins of particles be? Where can they exist? And once you've figured out those states and the energy levels that correspond to them, you can evaluate this partition function and work out a hell of a lot of things about the system that way. So, for example, in magnetism, quite often they work out the energy of the microstates based on this idea that nearest neighbour atoms are interacting with each other. A huge amount of condensed matter physics, which predicts the behaviour of materials, can be derived by applying these models and their partition functions to real systems. It leads to all kinds of incredible results. You can find the behaviour of all kinds of particles, quantum particles, by putting in information about Pauli exclusion, and it can give you models of the behaviour of quantum matter like superconductors and superfluids. You can even expand it to understand how things like phase transitions between solids and liquids work. It's a truly incredibly powerful, mathematically beautiful, and extremely useful theory. The reason that it's so wonderful is because, for once, it actually provides you with a nice set of things to do when you encounter a new physical system. You have a recipe, an algorithm that you can go through to try and figure out how this system is going to work. You just figure out what the microstates are, what the energies would be, and then you can describe how it will behave at different temperatures. You can describe, for example, for that 2-level system, what probability it is to flip at a given temperature. You look at the interactions between parts of the system to calculate the energy terms. So you can see there's a nice analogy here with Lagrangian mechanics versus Newtonian mechanics, which we'll talk about in the episode on Lagrangian dynamics. Basically, Lagrangians use energy to analyse systems, while Newton's laws use their dynamics, ideas of force. If you apply that to a big system with a lot of parts, like molecules of gas in a box, then you have the choice between statistical mechanics, which uses the energy of systems to constrain them, and their thermodynamics and entropy essentially to analyse them, versus kinetic theory, which tries to work things out in terms of forces and averages for the dynamics and motions of that big collection of particles. Just like Lagrangian dynamics, the statistical mechanics of systems can often be far more elegant and useful than its more dynamical and more brute force counterpart, where you're trying to figure out the motions and trajectories of individual particles. It works so wonderfully for these simple systems and usually produces results that fit with your intuition, such that any young physicist who really starts getting into statistical mechanics is just staggered by how neatly everything tends to work out and how useful the partition function ends up being. A far cry from Boltzmann and Ehrenfest getting depressed about the consequences of their work. So that about wraps it up for the briefest of introductions to statistical mechanics, the theory that Boltzmann and others developed, this strange, wonderful marriage of probability theory, thermodynamics, and entropy. I know that this was a little strange for an episode because I was basically describing the kind of maths that you can do rather than describing the physics. That was mostly covered in the second law episode, but I just hope that I've given you a tiny flavour of the wonderful and vastly underappreciated field of study, although not amongst physicists. Plenty of people talk about relativity and quantum mechanics, but I bet way fewer know about statistical mechanics, even though it's in many ways just as beautiful and elegant. The idea that entropy is always maximising itself in equilibrium might have driven Boltzmann to despair, but it turns out to be very useful for our calculations. So the heat death of the universe comes with some small consolation prize for understanding how it works while it's still here. Thanks for listening to this episode of Physical Attraction. Remember, you can find us on the web at physicspodcast.com. There you will find the contact form, the Patreon, the PayPal. There's plenty of ways to support us, get in touch, let us know what you think of the show, comments, questions or concerns. I always really enjoy hearing from you guys, whatever you have to say. On Twitter, PhysicsPod. On Facebook, Physical Attraction. You can find the articles I've written over the years at Singularity Hub, and the thing that we mostly ask you to do for the show to help promote it is to tell at least one other friend who might be interested in the episode about it. Let them know, expand the audience, keep it going. I'll be with you soon for another episode. Until then, take care.